All right, back recording. Right, so you guys just saw a short video on this. Hopefully, clear that up a bit. Okay. All right, so a couple things left here. Let's look at mass energy equivalence. Okay. So if you look at both those equations of special relativity, like that one for momentum dilation, you could do a proof and show like the base energy of any mass. Right? It ends up being this equation right here. Okay. Uh, Now, P represents the momentum of a particle. So if something's at rest, then the momentum of that particle would be 0 kilogram meter per second. So you can scratch that term. Then you can square root both sides and get, oh, this right here. Look at this. E equals mc squared. You guys have seen this before. You guys remember I was telling you that the energy associated with some mass. Right? This is the energy of nuclear reactions, right? This is also called mass energy equivalence. Right? Mass energy equivalence. Right? Now, what's kind of weird in a way is that mass in kilograms and energy in joules, those are completely different units. So at an outset, they seem like completely different concepts, right? So energy in joules, mass in kilograms, c squared is the speed of light squared. Right? This says that mass and energy are effectively two sides of the same coin, right? And this is the energy, again, from of nuclear reaction. So whenever you run a nuclear reaction, there's missing mass. Where does that mass go? It goes into energy and then run power plants, that sort of thing. Right, and finally, general relativity. So everything I've been telling you guys so far is just special relativity, right? That's 1905 that was published. Right? Many years later, 1915, I want to say, Einstein published a paper that also incorporated mass of particles. Okay? Now, do you guys remember from Newtonian mechanics? Suppose you have like, I don't know, maybe the Earth and the Moon, for example. Mass, mass. There's a distance between the two. They will call it R. And there's a gravitational force between the two. I'll call it F, right? Equal and opposite forces, right? And Newton said that that force was equal to GMM over R squared. That's what Newton said, right? That's Newtonian mechanics, right? But Einstein before Einstein, there were some problems with this. I remember one problem was if you look at the orbit of the planet Mercury, it doesn't follow exactly what Isaac Newton would predict with his orbital mechanics, right? So this starts to break down in a few places, right? Einstein says, "Oh, actually, I have a solution to that. Right? I can expand relativity to also include mass, right? And from this point of view, space-time is this four-dimensional fabric where if you follow Newton's first law of motion, things want to move in straight lines, but things are moving in straight lines on a curved space-time fabric. So whereas Isaac Newton explained maybe the moon orbiting the Earth because there's this gravitational force that's moving to the side. That's the way I taught you last semester. It's like a centripetal force. This gravitational force is acting as a centripetal force. Okay. Einstein says, no, actually, the moon is only ever moving in a straight line. But the spacetime is curved due to the presence of a mass, right? And you can calculate what it's going to be. Okay? Now, there are plenty of experiments to back this up. I mean, this is well founded at this point. But one of the first experiments that really validated this was a solar eclipse in 1919. Okay? So now, why a solar eclipse? What's special about this? Well, think about the sun. Right? The sun is by far easily the most massive thing in our solar system. Something like 99% the mass of the solar system. Right? So if there's going to be any kind of what's called gravitational lensing, right? Gravitational lensing that's really observable. Well, it'd be nice to see if it's around the periphery of the sun. Like, what if you knew the stars that should be behind the sun? Because you know the night sky, right? So there should be some stars here. Maybe like this one we should be able to see, right? And if this gravitational lensing really is true, and it's exactly as Einstein would have predicted, according to these equations he's writing down in 1915, then they should be shifted a little bit out of place. Problem is, the sun is so bright, how can you really see those stars in photograph? During a solar eclipse. Turns out that the moon can just barely cover the sun from our point of view. It has the same angular size in the sky. The sun has 400 times the diameter, but also 400 times the distance. So in 1919, the moon comes right across the sun. Some photographers take pictures of these stars. And in fact, the stars were shifted exactly out of place as Einstein predicted they would be. Again, there have been a lot of examples of general relativity in the meantime. Have I told you guys about dark matter yet? Dark matter and dark energy? Okay, all right. So that'll be coming up sometime this week. I'll tell you guys about dark matter and dark energy. Okay, all right. But bell's about to ring, so that is a wrap on today.